And get started. Okay, good afternoon, ladies and gentlemen, graduate students, and a couple of my colleagues. Welcome to our very first graduate seminar for this semester, spring 2023. I'm very pleased to welcome my colleague, Dr. Brian Wisner from Department of Mechanical Engineering at Ohio University to join us for the very first talk of this semester. I'm going to have a quick introduction about Dr. Wisner. I have a brief write-up here. Of course, it was a long history of your educational background, Dr. Wisner. I'm going to make it shorter in the interest of time. Yeah, Dr. Wisner got his master's, PhD, and his postdoc at Drexel University. For his PhD, he focused on microscale sensitive non-destructive evaluation, or NDE. He has also been involved with industry, including Army Research Lab and Sandia National Lab during his PhD, and also after his PhD during his postdoc. In 2019, he joined the Faculty of Mechanical Engineering at Ohio University, and his work is on the same field, non-destructive methods, and also additive manufacturing. He has projects ranging from fatigue damage detection using non-contact acoustic sensors to altering grain structure with ultrasound. It could be interesting for the audience that Dr. Wisner and I are working collaboratively on a project. Hopefully, we are going to submit an NSF proposal sometime soon. I guess, Dr. Wisner, we met each other first in a conference, right? In one of these TMS conferences.
Yep, right? TMS, yep.
Very good, very good. This is the beauty of conference and collaboration and shaking hands.
It is.
Very good. Thank you so much. Without further ado, I give the floor to you, Dr. Wisner. Audience, if you have any question, stick with your question until end of this talk. You can turn on your mic at the end of the talk and ask your question, or there is a chat box here that you can put your question here, and I will read it out loud. Thank you so much. Dr. Brian, all yours.
Thank you very much. Thank you for that introduction. So yeah, I started at the Mechanical Engineering Department here in 2019. And I'm gonna give you a little bit of background about Ohio University and kind of how my projects have shifted before I jump straight into them. But the focus of this talk is really using non-destructive evaluation across different avenues. So manufacturing, energy storage, damage detection are three of the major areas I focus, but it's not exclusive to that. So let me see if I can get my, there we go. So Ohio University, for those who aren't aware, it's in Athens, so Southeast Ohio. It's a beautiful campus here. So jump into that. There's a bunch of departments, centers, and institutes that we have at this institution. Mechanical engineering itself houses Center for Advanced Materials Processing and the Institute for Sustainable Energy and the Environment, both of which I am a part of, and some of these projects are tied in with those centers and institutes. My current group has 5 graduate students, 4 PhD, 1 master's, and 1 recently graduated master's student. And I also rely a lot on undergraduate student research. So some of the projects you'll see were actually conducted by undergraduate researchers. Center for Advanced Materials Processing is where you'll see most of the work. This is the one that focuses on additive manufacturing. And while my non-destructive evaluation isn't exclusive to camp, it is where a lot of that work exists. And then there's also the Institute for Sustainable Energy and the Environment, and primarily I work with 2 faculty over in that department, in that institute. And that you'll see is where we're focusing on the energy storage systems. So some of the collaborators, this was mentioned previously on these projects, previous institutes I've had. I do a lot of work with Texas Research Institute from Austin. Arctos is a primary funding source for Air Force Research Lab for us. But we've also done work with Sandia. We've done some work with NIST, and we are also now part of America Makes for the additive manufacturing side of things. So what I'm going to focus on here is broken down into the motivation kind of behind the research I do and why I approach it the way I do. We'll talk about what that approach is. And then I'm going to focus on 3 major areas of research for us. The first, which we'll spend most time on, is fatigue damage detection. Second, we'll talk a little bit about microstructure refinement in additive manufacturing. And then the last is our most recent project, which is trying to detect defects in batteries, specifically for electric vehicles. So my focus really is understanding material behavior. So my group, I actually named Mechanical Behavior of Materials Group for a reason. We're truly just trying to understand how materials respond, and we're trying to do this across length scales, across modalities, talking about full structures, talking about the microscale and how that affects and causes the full structure to behave the way it does, what we can do to modify that through the processing methods we do, through altering existing processing methods, and really looking at how this non-homogeneous structure gives us these properties that we're trying to work with for design. And that's where we really focus. And to do that, we realize that we kind of have to bridge scales. So if we're worried about how a structure is going to behave, we have to realize there's plasticity, crystal plasticity involved with that. There's dislocations. If it's a metal, you can have both patterns and discrete locations, and even down to the atomistic level, ultimately controls, as you work your way up, how the material responds. And that means we need different methodologies in order to test and understand and visualize and see what's happening at those different scales. So that leads to the question of, what are we monitoring? How fast do we have to monitor it? Because this could be across time scales as well. And where is it likely to happen? So the approach we take kind of leverages a number of tools. I'm just going to throw them all up here to be a little bit faster here. So we have small scale testing capability, and we can put this thing under a microscope that allows us to see microscale evolution of a material as we're applying loads to it. And that could be tensile loads, compression loads. This particular device can do fatigue, but it is a much lower cycle fatigue. And then we apply techniques like optical metrology. Primarily, we do something called digital image correlation, or DIC, which allows us to obtain strain maps as we're applying the load, and acoustic emission. There are primary methodologies. They are not the only ones we use, but through a lot of experience, we found that the surface information from DIC and the volume information from acoustic emission tends to give us a fairly good picture of what's happening without having to put a ton of sensors on this. And I'll show you examples of how all of these are used in a more detail later. And then we add into that machine learning and AI. And that's because, just if you think about acoustic emission, this bottom right plot in the AE section is an example of the type of data you get from one monotonic load test, about a 5-minute test, and we have all of these dots. So we have to come up with some way to handle that and be able to get meaning out of it in a reasonable time frame. And we're actually developing, this is actually a microprocessor all based on Raspberry Pis built in our lab upstairs that allows us to do this type of a processing as the data is being collected. And what do we get from this? Well, if we combine the non-destructive testing, it could be ex situ methods like X-ray analysis or some of the nano indentations that we're trying to get some understanding of the material, or in situ like the DIC, which in the previous case I showed you a coupon scale. In this case, I'm showing you if you use DIC from SEM images, you can obtain information about the particles and how strain forms around it, or dislocations. And acoustic emission, microscopy, whatever you're measuring as you're collecting data, the loads of the data themselves, and then try to understand what is the damage, as I call them now, damage precursors that are going to lead to how this material ultimately fails. And we can do this at the microscale, and we can go up in scale, whatever scale you want to from there. And that means, as I mentioned before, leveraging all of these. And the machine learning algorithm we currently employ is a concept of data normalization, reduction, and feature selection, and then clustering, both unsupervised and supervised methods, along with outlier analysis, with an end goal for fatigue is our primary function here, to figure out how much life is left within a component. And that involves us taking acoustic emission, which is a wave, and extracting a bunch of information, tying that in with the DIC, tying that in with the microscopy. So none of the techniques that we use can be used on its own. It doesn't give you the full picture on its own. And that's the emphasis that we're trying to get across with this approach. So let's see that applied to a couple of different situations. So fatigue damage detection first. We have a couple of methodologies associated with here. There's one that I actually don't have a picture of right now. That is a newer methodology that we have developed here at Ohio University. But what you see in this case is on the left, we have what's considered free vibrations testing. This was developed at AFRL, and the laser, which you hope you might be able to see as a red dot here, is what's actually doing the monitoring on the sample. So we don't actually have to make contact with it to do acoustic emission. On the right-hand side, we have a vibrations similar concept, but instead of using what they consider free, using a Krauss geometry. Both of these are designed to try to mitigate and reduce boundary conditions in the sample. So in the one on the left, this hangs from a fishing line, and a solenoid vibrates the material. In the case of the one on the left, it's using geometry to create a gauge section that is free from the effects of the clamping section itself. We've since developed a methodology to do this kind of a loading with axial loads as well. And that allows us to test different modalities on the same shaker, which is quite beneficial. Traditionally, though, acoustic emission is done with traditional sensors. So I have here that we're talking about advances going to laser. What we want to see with this is a traditional acoustic emission system, for those who aren't aware, consists of a DAC, which is essentially a computer. And this actually operates as its own computer as well as DAC. A preamplification system, in this case, it's a simple box, and some kind of a physical sensor that you make contact with the material. And to do that, you typically will either put it on with something like a vacuum grease or a glue. But what this means is you're physically contacting the material, which in the case of certain applications such as high temperature, as high strain rates, as dealing with very thin films, either is not practical or can be a potential issue in causing a change in how the material responds. And for that reason, we've explored replacing these with a laser vibrometer so that we can do this without actually making direct contact, physical contact with the material, and it allows us to get acoustic information on test regimes that otherwise is not a practical solution. So the first takeaway from the talk I'm giving today is that traditional acoustic emission can be used to detect defects, and it is scale independent. So what the same sensors that we use if we're trying to find macro cracks, large scale defects, we can use those same sensors to try to find small scale defects as well. The trick is knowing what the level of noise you have is and what the defect sounds like to be able to identify it. For example, this is a study that was done back in 2018, where right before I left Drexel, we've done this here since, but this is still some of the best results I've obtained, where if we look at this image, there is a difference in grayscale. This is an aluminum 2024 series alloy that we zoomed in on, and we applied a nano indentation directly on one of the precipitates. In this case, it's actually more of a particle. It's a little bit larger than a typical precipitate. And we initiated this fracture event to happen and recorded what that signal looked like. We did the same thing indenting straight on the aluminum matrix itself, and we observed a much different response, order of magnitude weaker in the burst characteristics and the frequency content. So very different signals indenting the same material in just two different locations. And by doing that, we could take that information and apply it to something like this. So this is actually fatigue data from the same material. And what we can do is look at the characteristics of what this upper wave is, its frequency content, the fact that it's a burst signal, it grows and decays pretty quickly. And we can use that to say that if we see something like this, more than likely, it is some kind of a brittle fracture event. And by doing that, we can look at what's happening here and recognize that there is a separation in these features. And by doing that, we can say, well, anything that's in this 500 kilohertz range is probably fracture. And not only that, but we can see how that changes over time. And so in this case, we're seeing a lot of activity early that kind of decays out. So it seems that you just by doing a very simple analysis like that, you can determine if there's a change in the damage mechanisms, in what's happening inside your material, even if you're not looking at the same spot that's happening. Now, we can also prove this by looking at that response and then going around and searching the structure to try to figure out where the defects happened. So in some cases, we can observe particles and see them as we apply cycles, see them actually fracturing as they grow and how that grows. In other cases, excuse me, like the case where we start to see a change, we don't have these 500 kilohertz anymore. It seems to have reduced in content. We can actually map that to when a crack starts to grow, a macro crack from the edge of the sample. So the methodology works at that small scale. But we're not limited to just fatigue test, to monotonic, to load, to doing this by hand. We can see that separation. We see trends as they're happening, but we can really zoom in on certain effects. So looking at the AE, we can see with load curves, there's a change where the yield's happening. We can see a lack of activity before, only a little bit. We can see a growth of activity after. We can start to connect how the material is responding with only using sound. We're just listening to this material as it deforms. And we can go in and pull some of those waves out and see what they look like. And we can see that if we look wave A, B, and D, these ones that have higher amplitude, and the one compared to the C, which is a lower amplitude, those have that burst characteristic, but they don't all have the same frequency content. And what that means is that they're likely some kind of a damage or a fracture type event, something that's instantaneous release of energy, but not necessarily the same source. So maybe it's not a particle fracture anymore. Maybe it is a fracture of the aluminum matrix itself. Maybe it's the particle separating from the aluminum, a debonding type procedure. So if we take that and we realize we did all of that just by observing what was happening and trying to connect that to what we saw with acoustic emission. But that was looking at individual waves. If we want to understand this on a more global scale, we need to bring in machine learning. And it is not only powerful, but critical when we're talking about acoustic emission monitoring if you want to have any semblance of understanding of a longer test or of a material that produces more energy or produces more signals. Composites in particular tend to be very, I like to use the word talkative, because they produce a lot of acoustic emission, but because of that, it's hard to process that unless you're doing something like a machine learning tool. And so what we can do is take what we learned looking at a few waves and kind of extrapolate that. So if we look, what I'm showing you here is that same basic test from before. We have a monotonic load on an aluminum sample. We have data that we collected in acoustic emission, and we performed a clustering method. In this case, it was using a k-means, simple k-means clustering, using about 7 of the features that you can use to describe a wave. And we identified 3 clusters. One with a high amount of amplitude, reasonably amplitude, one with a peak frequency content, that 500 kilohertz range, one with a content down around a little bit below 200. And then there's the red clustering that really is just extremely loud signals. And we're able to plot how this evolves over time and connect what we know from in situ observation of the damage with the acoustic emission monitoring to hypothesize what each of these clusters might be representing. The easiest one is the red dots that only happens right at final fracture. That's the one simple enough. That is the final fracture. What's more challenging is getting into the green and the blue dots. And that's because if we look at them, they don't seem to be, there seems to be a number of different bands within each of these clusters. So the clustering may not have been the most accurate to identify every last source. But what we do know for sure is that your green cluster is more likely to be some kind of a damage than the blue cluster is. It's not to say the blue cluster doesn't contain some level of damage, but it's less likely to contain the damage because it has significant frequency content in the same range as the operating machinery itself. So the DAC that we use to collect this data has an operating frequency that can bias the signal to about 150 kilohertz, and that's about what you're seeing here. We can then extend this and plot it in different forms and kind of see how different frequency contents exist. We can do it in fatigue tests, where you can do this across any loading scheme you want to do and try to understand how the material is evolving. And what we can see is, as we look through this, there tends to be a shift in cycles from certain mechanisms like the green, which is more dominant early on, to the blue, which is more dominant later on. And tying that back to the microstructure now, there is the potential to make an argument that the green may represent nucleation and the blue may represent growth. Without direct observation, that is a difficult argument to make, at least until you've done it a few times. But the power of machine learning is it gives us the ability to see these trends, which we can then take and try to leverage against what we're trying to understand, which is how the material responds to load. So, acoustic emission can be used to detect crack nucleation and growth. We saw that a little bit before. We've seen that when we originally acquired the data, trying to go hunt for material or for where the crack is. We've seen it when we're starting to leverage machine learning to see how the trends are evolving. But we can do that across other modalities. So everything up until here was a straight monotonic, just I'm pulling the material. Or I'm doing a cyclic loading on an Instron machine or an MTS, low cycles, slow loadings. This is an example of the type of data you get when you do the same procedure on one of those shaker systems I showed you earlier. So when we do that, what we have to realize is these are physical sensors that we're currently using. So if we put a physical sensor onto a material and shake the material, we're going to get a response in the sensor that is just the operation of the machinery. It is not any indication of damage. But if we put a device on there, and so we did this by having a sensor mounted directly to the shaker and a sensor mounted to a sample on the shaker. And by doing this, we're able to see what the shaker produces as far as noise in this sensor, and then remove anything below that line. And what that tells us is when we're talking about amplitude, how loud the signal is, the machine we're using, anything on the order of about 52 decibels or lower has the potential to be just the machine in its standard operation. Anything above that 42 decibels doesn't exist on the machine, which means it has to come from the sample. And that's where the information for damage comes. Now, if we look at the data on the right, this is the raw data collected. We're getting a bunch of noise from the machine. If we put that 42 decibel cutoff on it, we still have some information early. We definitely have information as we get towards the final failure of this sample. So we lose information likely because it's noisy. We're throwing away information just by using a threshold method, but we still get an idea of what's happening. If we wanted to, there is the potential to employ denoising algorithms such as wavelets, denoising, or just straight up Butterworth filters that can help a little bit in order to try to back out and see if any of these signals below the blue line contain damage information. What typically you'll find is, yes, they contain some damage information, but the general trend, whether I include them or not, remains about the same. And that's where we can then start looking at the data just above the line. And that allows us to, instead of having to deal with all of those signals, we can work with a much smaller data set and still get the same basic trend information that we're looking for. And we can see more activity early, dies off a little bit before a crack nucleates and really starts to grow rapidly across the material. Not surprising for a bending fatigue test. And we can do this both in terms of amplitude, weighted peak frequency, absolute energy, any metric you want to take a wave and quantify it as a single number. You could look at this in order to be able to see what's happening. And then we can go under the high-speed shaker and kind of zoom in and see what these trends are. So I've shown this plot a few times. At this point, I kind of want to emphasize why. This is rise time versus duration. So rise time is how fast the wave reaches its maximum value, and duration is how long it goes from when you first see it to when it stops. For a lot of materials, if you're looking for a fracture event, that should be a fairly fast event. It should not take long to reach its peak, and it should not take long to die back down. And that means all of those waves for a fracture type event should exist down in this low rise time, low duration area. And then as you move away from that, you can start to introduce other mechanisms, more of a growth response, a longer crack increment, potentially fretting, anything else that might be producing an acoustic signal. And by doing that, we can see that what you'll find when you monitor this is all of these early ones actually have a decent amount of energy, and most of them happen at the beginning of the loading, whether it's a monotonic or a fatigue test, particularly in low cycle fatigue test. This is the area, this low corner here, that you get all the dots at the beginning of your experiment. After a period of time, they shift away from this location and start to fill up other areas. And so you can very simply mark a transition in damage mechanisms just by where you're getting your dots. It's a quite powerful method that is actually fairly simple, which is nice. So just some examples of the waves you get from the high-speed shaker. I mentioned before that it's a noisy system. So what I'm trying to show you here is that even with a noisy system, the waves from damage are actually quite impressive. So you can see them pretty well, even amongst all of that noise. However, there are others that you have like this that aren't quite so burst and die down. They kind of exist for a while. That can also color the results a little bit. So something that we always have to watch out. Now, what this takes us to is this was all done with contact-based sensing. And I want to give you that frame so that you can understand what the results kind of look like from it as we move into non-contact methods. So there's two kind of modalities that are explored in this non-contact acoustic system. One is straight non-contact sensors, sound-based sensors. You can think of like a microphone. That's effectively how a non-contact traditional sensor would work. It's collecting the signal and bringing it in. The downside to that is you're trying to transfer sound from a metal through air into your sensor. And by doing that, the air can act as a huge dampener. And so you lose a lot of your information. But if you change your methodology and you use something like a laser vibrometer, you're still detecting the surface. You're not making physical contact with the surface anymore, but you're detecting the surface itself, which means we don't have to worry about losses traveling through air. And that's the methodology that we're approaching. And this came around because we've been trying to study some thin film samples with AFRL, and they are interested in the acoustic emission response of it, but we can't make contact with thin film and shake the thin film without the mode shapes, without all the mechanisms changing. And so that's where the laser came in. And what's nice about this kind of a methodology is the laser, depending on which one you acquire, will capture a larger range of frequencies than any traditional sensor can. So a traditional sensor on the order, you can get some that are considered wideband that can get maybe 100 kilohertz to 2 megahertz. There's some that can go a little more than that. But the laser, the one that I'm using, can go from almost 0 hertz up to 24 megahertz. Now, the test that we're running right now is 1 megahertz that way, because that's in the range of one of our sensors, so we can compare traditional PZT sensors to our laser method. But we're not limited to that. And what that means is we have the ability to acquire what you see on the top right and the bottom right. The top right is the vibration I'm applying through the solenoid in order to cause this material to bend. I can monitor that throughout the entire test, and I can monitor the acoustic emission, which is the bottom right, the higher frequency content, throughout the entire test. And I'm doing this with a single sensor. One laser can do both. I just need a filter to whichever range I'm looking for. And that gives me the ability to do traditional fatigue process. So if you think about traditional vibrations-based testing, it's resonance-based. A material has a resonance, and as the material damages, that resonance changes. And you'd be able to see that in this top plot as we continued loading. That being said, I could at the same time be looking at acoustic emission. And what's unique about this is this top plot at this point, for this particular example I'm showing you, you cannot see a drop in amplitude under the applied load, which means as far as the global material sees, it's not damaged. But the acoustic emission is showing activity, What this tells us is there's microscale damage happening to this material that is not enough to yet affect the global properties. But eventually, as the more acoustic emission, you see more of this happening, that's going to indicate more and more small scale damage that will eventually accumulate enough to finally affect the large scale behavior. And that's the power and the benefit of AE. Now, I showed you waveforms before from what a traditional PZT sensor looks like. This is what they look like from a laser. So they're a lot shorter, a lot quicker in duration. We've been doing some studies recently trying to determine what the ideal window size is for dealing with these kinds of waves. Do we need to get down to this small of a timestamp, or can we get away with taking a larger amount at one time? For crack growth studies, there seems to be ability we can go larger. If we're looking for some of the earlier damage, then we start to run into an issue if we try to change our window size. But even if we stay with a small scale, we can do things. So this was a fatigue test on a middle tension sample conducted on a servo hydraulic machine. And this was basically us trying to get the ability to start showing live extraction. So this is a controlled experiment where we know we're going to nucleate cracks and we know where we're going to nucleate cracks in order to validate our results. And the yellow line represents the first nucleation based on digital image correlation. We zoomed in, we found where this first crack initiated, and it happened right about this yellow line. So we see a bunch of activity. Each of these red dots represents one of these types of waves. We see a lot of activity early, kind of dies off right around where the crack's nucleating, and then we see more activity right about where that's not just nucleating anymore, but starting to kind of grow, and then it kind of decays again before building up right before final failure. And you can see that in the hysteresis loop, and I will apologize, these loops are very sparse. We only took 10 data points per cycle from the DIC, and we only did that every 100 cycles in order to account for the 7,000 cycles we're doing and not having too much data to process. But you can see in the hysteresis loop that we have little happening. We see it starts to deviate some as the crack is growing, and as the crack grows larger and larger, it starts to deviate faster and faster. The AE is reflecting the same thing. And we can do the AE without having to take images, which means less storage space, which is a huge advantage. Now, downside to anything to do with sound traveling in a material, there's a crack here, which means if I place my sensor next to the notch or above it, I will have different results, different waves. The trends can still be there, but what the wave looks like is different, and that makes it a little bit more challenging to make this methodology material and geometry agnostic. And that's ultimately where we want to go. I'm not going to spend more time on this. This is all about the same concepts, but what I do want to emphasize is the ability we have to start doing this in situ. So what I'm showing you here is on the left is the workflow that doesn't care. I can do that offline or online. The right-hand side is showing you the actual hardware architecture, and it's literally just a bunch of nodes through an Ethernet switch connected to a hard drive. And if we look at what that physically looks like, that's just this. We have, in this case, 5 Raspberry Pi nodes connected to a hard drive. One is the master, which tells the other 4 what part of the processing it needs to do. And we can actually put the laser directly into this processor system and do this processing as the waves come in, which means we can live detect damage evolution. And the other benefit and the reason we do microprocessors is its scalability. It's fairly easy for us to add another microprocessor, and it's not ridiculously expensive to do so. If we wanted to do this with more computer hardware, basically think about a PC, in order to add this, you're going to start talking about adding multiple PCs, syncing those together. That is a lot more costly than if we go with the microprocessor route. Even if we go with more advanced processors, as we're looking to start doing as we bring in the machine learning to the live analysis. So that's the fatigue damage detection. I spent a lot of time on there because that gives us a lot of the background for some of the rest of the talk that we're going to be doing. So we're going to focus a little bit on microstructure refinement and additive manufacturing. And then very quickly after that, we'll get to the battery defects. So the concept is this. The left image here shows a case where we have ultrasound on and off. What effectively this means is if you're familiar with 3D printing, particularly laser powder bed fusion, you have your build plate, you have your sub build plate, and then your apparatus that pulls that down as you build this thing layer by layer. What we're doing is we're sandwiching an ultrasonic transducer. So you can think those physical sensors I told that we use for acoustic emission, the same thing can actually send energy. So if you put one of those between the build plate and the sub build plate and send energy up through the build plate, you can affect things like the porosity in the material. And I will admit these parameters that were used here were not ideal parameters. The system that we use is a open additive Panda system, but it's a pre-Panda. It's a beta system, the second one they ever made. And so the parameters that they suggest for their pre-Pandas or for their Pandas don't work as well for this system. So we had to modify a little bit after we did this. But even with suboptimum parameters, supplying energy in the form of ultrasound through the material affects the cooling of the material, affects the grain structure, affects the porosity, and allows you to reduce porosity as compared to not using it. That can also affect the grain structure as you turn ultrasound on and off. So this is the premise of what we have. This is from a publication focused on direct energy deposition. We use a very similar approach, but we're not, in our case, we don't directly mount the build plate to the transducer. We just sandwich it between and mount on the sides here, and we have to add a gasket so that the powder does not come down through the sides. And what they found was that with UV, there's an increase in things like tensile strength, yield strength, ductility, toughness, all the things we want. There's evidence that suggests that you can do that in laser powder bed fusion as well in stainless steel. That was in 2020. Todaro in 2021 also again did this in stainless steel, looking again at porosity and grain size differences. So this has been shown to be feasible. Most of these studies do not use a full build plate. What they do is they take a transducer, create a sonotrode on top of it to increase the intensity of the ultrasound, and then build on top of the sonotrode. And that limits the size of the build you can produce. So what we've been attempting to do is see if we can get a similar result without having to use a sonotrode. And that's where this methodology kind of shows up here. So this is our actual structure, the ultrasonic transducer sandwiched between the plates. This is a traditional build plate, standard 6x6 build plate that we're sending the energy into. We did some studies across different locations on the build plate, the circle representing the transducer. So we have samples directly on top of the transducer and those next to the transducer to understand if we're clamping this into a traditional system, how is that affecting the ultrasound at different locations? And we actually used the laser I told you before in order to see what kind of energy we were supplying. So in this case, we're applying about 0.55 micrometers at the center with a 23.5 kilohertz actuation frequency. If we do that, there we go. If we do that, then we want to see, does ultrasound do this? And what we've discovered is that if you can supply sufficient energy, you can cause a shift from untreated elongated grain structure with the black arrow representing the build direction to a more equiax grain structure build in that direction with a reduction in porosity as compared to no treatment. Now, what we also discovered by accident on this when we set up one of our experiments is if you're not sending a high enough intensity, you will not see this grain refinement effect. But you will still see an increase in your material properties because you're affecting the sub-grain structure as you do so. So there's actually two effects that are going on here. And there is a publication that is in works addressing that should be coming out here in the next month or two. So what are the effects that we see? Well, in our case, we focused on hardness tests because we're printing Inconel 718, which is highly expensive. And so to get an idea of property shifts, we're focusing on the hardness and going into small scale testing so that we can get properties without having to use a large amount of powder. And what we see is an average hardness increase of about 5 points on the Rockwell C scale and a tightening of the standard deviation. So not only is the hardness going up, but the variation in hardness across the sample goes down. which is a nice benefit that we can get. And if we quantify some of the properties in the grain structure for high enough intensity, you can very easily see that the ultrasound ones, which are represented by the red, and the non-ultrasound represented by the blue, there's a shift towards the smaller diameter grain if we take that area and assume that's the grain. Same thing on aspect ratio. There's a shift down to a 0 aspect ratio, getting closer to equiaxed grains, not exclusively, but more consistently. So that leads to the lower intensity, ultra subgrain structure. So this was tested both on and off the transducer. So I showed you we did studies where samples were directly above the transducer and studies where they were off on the side. Both showed an increase in hardness, but those that were on the actuator showed a better increase in hardness. And we saw that across both global scale hardness, or a Rockwell scale, and across micro hardness. But looking at these images, very, very little difference in the actual grain structure itself. It all ties down to this, which is the spacing of mostly your Lave's phase, but your sub grain structure that you see going on here, they're a lot more evenly dispersed, a lot less variability across the sample. And that leads into the battery defect monitoring, which is very quick, as we are just starting this, but I'd like to show that the methodology I talked about for damage detection, altering metal microstructure on additive manufacturing, can be used for almost anything you want. And in this case, we have batteries. And so we have 3 batteries that we're testing. One that is pristine. We got it. We did not charge it maybe once, and just to see the effects there. We have a battery that we charged in negative 10 degrees Celsius, and one for this result that we charged in negative 20 degrees Celsius, trying to cause damage in the battery. We have since done one, I don't have the results on that yet, we're still processing them. We've since done one at negative 40 degrees Celsius to see really how bad that was, and we actually monitored the acoustic emission as the battery was charging, and we're able to see damage happening as we charge the battery. So I don't have that newest results to show you, but what I can show you is that if you look at the raw data for the same points in the grid structure for a pristine battery and a damaged battery, there is a shift in time of flight. So we can measure, we're sending a known signal. We know how long it's going to take to come down and come back through the material in a pristine condition. As the material degrades, that time of flight typically elongates. It gets longer. And so we're seeing that in a damaged battery. So what the whole goal of this is to detect damaged batteries that are coming out of electric vehicles and seeing if they're too damaged to be repurposed, or if they're okay for us to repurpose for a new use like grid storage. Simultaneously, we're exploring the ability, can we detect batteries degrading during use so that we don't have to do this after the batteries go out of their life cycle. So that leads to the conclusion, which I'll leave up here as we do any questions people might have. But again, it's focusing on the concept that we live at the micro scale, the macro scale, trying to understand the bridge between them, looking at experimental and some computational. I throw that in there. I don't have a ton of computational results in this talk, but we are exploring using computations to help us understand what's happening with the additive manufacturing grain refinement studies. And so the whole approach that we take is bridging scales, both time and spatial scales, as well as experimentation and computation in order to understand materials. And that's where I'll leave it.
Perfect. Thank you so much, Brian, for the nice talk. I personally very much enjoyed it. Whenever I hear the word ultrasonic, I feel I like it because we, as you know, we are working a lot on ultrasonic fatigue.
Yeah.
Yeah, it's a very interesting talk. I feel a lot is going on in your research lab in terms of the capabilities of AE especially AE in additive manufacturing and also ultrasonic in additive manufacturing. Excellent talk. Thank you so much. Okay, audience, the floor is open to you. If you have any question, please feel free to turn on your microphone. If you are comfortable, you can ask your question directly from Dr. Brian. Otherwise, there's like a small chat box here in front of me. I do not see yet any question. If you have any question, feel free to put your question here. Yeah, I already received one question from Amin, a graduate student in our department. He, of course, thanks you so much for the great talk. He wants to know why your developed fatigue damage monitoring equipment work perfectly only for low cycle fatigue regime. Do you mean that that will not properly work in other regimes of fatigue, including high cycle and very high cycle?
Yeah. So the reason it works in low cycle fatigue is because that's all we've tested so far. So we're developing the system. So we have to, right now, because we're trying to develop this to do it live, we have to process the data twice. Once as it's coming and once to verify against existing methodologies. And because of that, it is time consuming. So we started with monotonic. We've done low cycle fatigue in order to get enough data sets that we can get some confidence that our process is working, not just on one case, but others. And then we are working on actually expanding that. And that's a piece of actually the proposal you and I are working together on, is getting some funding so that we can run some of those samples at higher cycles. So that is the next step, is to go to high cycle, then very high cycle, then ultra high. We want to go the whole range. But so far we've only done monotonic and low cycle fatigue.
Very good. Very good. Thank you, Brian. And the other question again, Mohsen is asking again, he's thanking you so much for the talk. He's asking for digital image correlation. Do
Yes.
you use any commercial software
Yeah.
or do it is done by any programming?
Yeah. So in my experience, I've used two. At Ohio University, we have a system called Aramis. It's produced by GOM, who I think is now owned by Zeiss, if I recall. So we use that system, and that's just because I'm partial to it. I understand it because I used it a lot in my PhD work. And they have a good collaboration with universities as far as educational experiences. And so from that perspective, we use them. And so we use their software for most of the processing. And we've done that with their camera system. So I have their stereo system that we use, but we also collect images through our own microscopes or SEMs. Whatever camera you want, you can use their software in. And for anybody who's interested, they actually have a free, it's called GOM Correlate. It's a free software that you can actually use for any images you have. It's not paid, so there's limiting factors to it, but it is available. The other one that I've used, and some of the results from here came from AFRL uses something called Correlated Solutions, which is just another competitor for GOM. GOM tends to focus on industry a lot more and academic partnerships and building that kind of a knowledge. Correlated Solutions focuses a lot on fundamental research. So I've used both. They have the benefits in different situations. I did not do any of the coding of it myself because we have ability in their software to design any testing regime we want. We can control how we take images through Python codes. It interfaces with that. So
perfect. Yeah, his question has a second part. The second part of the question says, most of these volumetric AM defects, like lack of fusion or gas porosity, are internal defects. The question is, how does the AE predict them, or just we can monitor the rate of weight growth in the part?
yes. So the key to acoustic emission, which is why I love it, is damage can happen anywhere in the material. And as long as there's a change and it releases energy and you have a sensor close enough that it will travel to it, you can detect it. The cool thing about what we're doing is we're sending ultrasound through the material to modify its structure, which is the premise of ultrasonic testing, which is the active form of acoustic emission. So we have two benefits here. One is if a stress crack, so a thermal crack forms, that releases energy that we can detect by the acoustic emission no matter where it happens in the material. Metals are very conductive of these waves. It'll travel plenty far enough for at least for a 6x6-inch build plate of relatively simple geometry. The other benefit is we're sending energy through. So we know the material we're building. We know what its wave speed should be if it's built well. So we know how long it should take us when we're at every layer to receive energy from when it gets sent, which means if we see a change in that, we know there's a buildup of porosities, a buildup of defects. Depending on the frequency of the wave that you're sending, you can see small defects or large defects. The 28 kilohertz we're using is only for large defects or large amounts of energy. So the other benefit of this is we would have the potential to use a transducer to affect the grain structure and a second source to actually look for defects. We have not done that yet, but that is the direction we're trying to go with this work with one of my PhD students.
Got it. Perfect. Thank you so much, Brian. Another student, Alariza, is asking, is AE only work in the air or we can use it for other environments? And also he's asking,
Yeah.
does it work for high temperature fatigue test as well or not?
Yes. Yeah. So the short answer is the premise, the physics of the technique work regardless of anything. The only limiting factor is your hardware to try to detect it. So historically, when you use contact-based sensors, there are things called waveguides that are used to get signals out so that it can go. Your waveguide's typically a metal cylinder, and what you're doing is basically just making it long enough that it gets cold enough you can put your sensor on it and still detect what's happening. Now, the waves you get are going to be different. You have to go through the waveguide theory. We have to go through all of that. You still get the activity. The processing and analysis is a little more complex. The idea behind air-coupled sensors is try to mitigate the need for that more complex analysis and detect the signal directly. So it could be air-coupled, or it could be through the laser like I do, are two of the current avenues to explore it. And the reason behind it is things like high temperature testing, impact-based testing. We've actually used our laser for a ballistics impact to determine whether there was full penetration of a material of interest. Because we didn't want to put a sensor in there that was too much energy, it would break the sensor. But we could put the laser outside of the gas launcher and actually shoot through acrylic and still detect the difference between a penetration and a non-full penetration.
Gotcha.
So there's a lot of potential for AE along these avenues for those applications.
Yes. And the second part of his question is, well, considering that ultrasonic fatigue is a resonance fatigue based, does this resonance interfere or creates any noise in
Yes.
AE? Yes,
Yes. So the resonance, if it's a 20 kilohertz and we know it's a 20 kilohertz, we can ignore all 20 kilohertz signals. Most of acoustic emission is operating above human hearing, well above 20 kilohertz. So we're talking hundreds of kilohertz or higher. That's not to say it all exists there. So we would be losing some information by neglecting certain frequencies. But most of the traditional sensors don't operate below 100 kilohertz or so anyway. There's a few that are in the 60s, a few into the 40s. But most of your wideband sensors don't go that low. So you wouldn't have that issue. Now, if you're using a laser, you would be potentially throwing away signals, but that's why I showed you could take the laser signal and you could actually separate out the AE. That's what, let me go back to that quick, actually. That's what this, where is it? This was bending, so it's not 20 kilohertz, but it's the same concept. In this case, we're applying, I want to say that was 400 hertz sinusoidal wave that we could pull out because we knew what that was. We could eliminate that, and that leaves us with just this bottom stuff, and that removes most of your noise. Yeah. The only other issue with ultrasonic, I want to emphasize a difference that we're doing with one of our methodologies. Is ultrasonic fatigue, you have to design a very specific geometry because your sample is resonating. The methodology we're pursuing is actually building a spring that's going to resonate and treat the sample as a rigid body so we can do alter the geometry. The downside to that is right now we can hit 1500 hertz, so 1.5 kilohertz. We can't hit 20 kilohertz from that, but it gives us ability to do different geometries. So the lower the frequency you're supplying, the easier it is to do this kind of separation. The higher that frequency gets,
becomes more challenging.
The more dangerous it is because you may be accidentally removing useful information.
Gotcha.
But hopefully not too much.
Gotcha. Well, I personally have two quick questions. We are getting closer to 2 p.m. And my question is that, well, you talked about all these nice things about AE. I'm just curious, what are the limitations, possible limitations of AE, especially in terms of fatigue damage detection?
The major limitation on acoustic emission comes from the fact we don't actually know the source. So these sources are happening, and what's happening is you have a damage initiate, which releases energy that's going to get convoluted as it travels through the material, convoluted with the sensor itself, convoluted as it goes through. So what you're actually getting as a wave is not the source. It's the source plus all of these other things. So you have to find a way to back that out. which means to get useful information about out of AE, it's really difficult to just stick something on there and get a result and be able to say that's what that is. For example, the battery results we're doing right now, we see activity. I have no idea what the mechanisms are that are causing it. I just know there's activity. So in order to make it useful, you have to bring in other methodologies or other ways. You have to do experimental campaigns to understand, if I see this wave, I know it's that. For example, the PhD dissertation you mentioned was really focusing on particle fractures. One mechanism, multiple years, in order to have confidence in that. Now, that was also developing the methodology to do the tests. So it won't take that long to do new studies. That's where the small scale testing really evolved. But being able to understand exactly what the AE is telling you is its biggest limitation. It gives you insight, but is not the best on its own unless you've done a large campaign and really brought in the machine learning and you have high confidence in it.
Got you. And one probably last question from my side at least is that in one of these case studies that you did and you applied ultrasonic wave on additively manufactured nickel, as far as I understood, all you saw was change in grain morphology, but no change in the grain size. Am I right or not?
In our case, so in some cases with higher intensity, you see grain size change more. In our case, we're not. So there's two theories about what's causing this to happen. One is that is cavitation. So there's wave streaming effects, there's cavitation, there's others. The prevailing theory is cavitation. It comes from casting theory, using ultrasound in order to get grain refinement in casting. It's the same premise that led to this. And so, to do that, if you use the same equations that they use to estimate the intensity needed to cause this, you would need significantly more energy. So for the case where we had grain shape change, we would just barely above what the theoretical cavitation threshold is for nickel 718. The studies that did this, where you can really see the difference in size, orders of magnitude above that point.
Okay.
And then the result that you see here, which is the last one, without this one, we were below the theoretical cavitation threshold.
Okay.
So it really ties into the intensity as to whether or not you see size change and much on the grain. So the lower the intensity, the more subgrain you change. As you increase intensity, you start to affect the actual grain size itself. And there's a balancing of energy from the laser that has to happen for this too.
Okay, very nice, Doug. Let me ask one more question. Brian, let's assume I'm a 3D printer manufacturer like EOS, and I want to approach you and ask you to put this device, ultrasonic vibration system, and install it on my 3D printer. How much cost would be added to my 3D printer?
That depends on the level. So this was actually developed starting from an SBIR, and it happened in COVID era. So we've been kind of piddling along after to get to where we need to be to get to the phase 2 point of this. But effectively, we approached it as there's different levels of this. The system that we used here, the transducer was about $100. You can actually get, it's the same kind of transducer that you have in an ultrasonic bath. You can put onto this thing. The controller for it was about $50. Now, the controller we have is one frequency, one intensity. So if you're good with just one frequency, one intensity, then you could probably get away with putting a system like this in on the order of a few $100s to a grand. If you want the control, which is where we ultimately want to get to with this, where you can change frequency and intensity, because cavitation threshold is dependent on those two things. The higher the frequency, the lower the intensity, you get the same result. Though there's a couple studies that show the end result is still slightly different. If you want to be able to change this for true tailorability, you're probably looking in the order of tens of thousands. But compared to the cost of the full machine, it's nothing.
Exactly. It's very much affordable, I guess.
Yes, exactly. Now, then there's the other thought that you could actually connect this to where the laser is and move the transducer and alter and get to really fine control to get some really, in order to do the complex geometries, you're going to be starting to rack this up. But if you're talking simple geometries, simple base structures, very simple controls.
Okay. Perfect. Thank you so very much. Is there any other question from students here? I do not see anything in the chat box. Again, one last call. If there is any other question, feel free to turn on your mic. Appreciate your time, Brian. It was a great talk. I really enjoyed it. I know you had a fairly busy Friday, this Friday. Thank you. I appreciate it. On behalf of other colleagues of mine here and also students, thank you and have a great weekend. I would like to end this session if there is no other question. And our timing was perfect. It's 2 p.m.
Beautiful.
Thank you so much.
Thank you guys.
Appreciate
Take
it.
care.
Thanks. Talk to you later.
Take
Bye.
care. Bye.